We're very happy this week to have our very own Alon Lavie as our speaker. Alon is a consulting professor at the LTI, so I'm sure that many of you know him. And his job, aside from that, is Vice President of Language Technologies at Unbabel. Unbabel is a company that has strong ties to the LTI. It was founded by an LTI graduate, Vasco Pedro. Alon and I go way back. We were pioneers in early primitive caveman speech translation starting in 1993, before we were even using statistical systems and not neural at all, but we were laying the groundwork and the demand for the ability to translate dialogues in the 1990s. And so and Alon, in the meantime, had his own company, Safava, that was then acquired. And so he's had a long time in industry and tremendous experience. And we're very happy to welcome him to give this talk on neural state-of-the-art MT evaluation. So thank you, and please start.
Thank you, Lori. It's such a pleasure to be back giving an LTI colloquium. I was trying to think actually when's the last time I gave an LTI colloquium talk, and I don't think I actually gave one during the time that I was at Amazon, but thank you, Lori, for that introduction and for taking us back. It's great to be among friends, particularly the faculty here. Most of the faculty still know me. You know, I was pretty much a full-time research professor at LTI for close to 20 years until I left for Amazon. The last few of those, as Lori mentioned, I was splitting my time between being a professor at LTI and a machine translation technology startup company that I started with a co-founder in 2009, and then was acquired by Amazon in 2015. And 2015 is when I actually kind of left my full-time position at CMU and opened, after that acquisition, Amazon's machine translation R&D lab here in Pittsburgh. So I brought them here to open a lab here. They're still here. They're growing very nicely. They're hiring. For those of you that are looking for jobs after you graduate. And then after I left there, about a little over a year and a half ago, I was really excited to actually join another CMU-rooted startup at a much more advanced stage. And that's where I am today, where I have been over the last couple of years. As Lori mentioned, my primary job these days is a VP of Language Technology at Unbabel, which is a language, an AI-based language technology and services company. And I'll tell you a little bit in just a few minutes and a little bit about what we do, to give you some context also to this work that we've been doing on a framework, a neural state-of-the-art framework for machine translation evaluation. And that title of consulting professor basically means that they conferred on me a very distinguished title of an adjunct professor. And I am around. I know during COVID, we don't see each other. So students here, probably many of the students maybe have never even seen me in the halls, but I do, before COVID, I was stopping by CMU typically once a week, and I do attend faculty meetings. I have been on thesis committees, and I'm still continue to be very much engaged and happy to even try and ramp up my re-engagement with LTI and all of you. So the work that I'm going to be talking about here today is part of the work that a team that I supervise at Unbabel does, that we're calling the Unbabel AI Metrics sub-team. It's actually part of our AI group at Unbabel. And so Unbabel, most of the teams, the technical teams and the headquarters is actually in Lisbon, Portugal. And two of the people that I've worked on this work here, Ricardo and Catarina, are two of our research engineers from Lisbon, Portugal. The third person is Craig Stewart, who is an LTI graduate, finished with a master's a couple of years ago, and join my team here. So before I even tell you specifically what I do, what Unbabel does, so in my role as Vice President of Language Technologies, I first of all opened a research lab for us here in Pittsburgh. I'm actually sitting in our office. As the background that you see, I'm sitting today in our office, even though, of course, because of COVID, our office is officially closed, but we have a faster and more reliable internet connection here in the office. So I thought I'd give my presentation today here rather than from home. So we're a small research lab right now. We're 3 people, all have actually a history, came out of CMU and LTI. And the goal is basically to do collaborative research wherever we can with LTI, with students, with faculty. We have an ongoing significant research project as part of the CMU Portugal program, where we just had a project meeting a couple of days ago, and that project is going really well. I'd be happy to, if there's questions about that at the end, I can address that as well. And lots of opportunities for collaboration, student internships, summer internships, students that are graduating that are interested in working in these areas. So I do that, and then additionally, I provide strategic sort of direction and help with running our AI teams also in Lisbon and managing our research projects that the AI team does there. So again, before I go into the specifics of the work that, the technical work that I want to describe to you today about Comet, just a little bit about Unbabel and what it does to give you context why this research is sort of so timely and important for us. So as I mentioned, we're fundamentally a translation technology and services, but we focus very specifically on large enterprise use cases for cross-lingual communication, and particularly communication scenarios related to things like customer service and customer support, but in general, areas that require basically solving the language barrier between enterprises and their customers, their clients, their groups, and their products marketers in different countries and different language speaking environments. And what's unique about Unbabel is sort of this combination of all of these different silos that you see here. So we're very heavily based on AI, proprietary AI technology, and leveraging state-of-the-art, particularly in machine translation, but also in other technologies that I'll show you in a minute. We combine that with a curated community of what we call editors, and these are primarily editors that edit the output of machine translation, and other linguistic communities that are necessary in order to support our operations. We rely a lot on proprietary data that comes from our customers. Along with our focus on AI, we build very, very strongly on continuous learning and continuous training of our underlying AI models. And finally, we have specific integrations with our enterprise types of use cases that make it seamless for our customers basically to use us and across language barriers. So what you see here next is basically the platform that we provide. So we provide a platform that solves basically end-to-end multilingual communication channels for enterprises. And that platform, this is kind of a typical workflow that you see through that platform, where we have some piece of content that's coming in that requires basically translation at the far left end. It can be a piece of structured content. It could be, a chat session. It can be customer support ticket or email, and it goes through this pipeline. This is just sort of the most standard sort of processing pipeline. It goes through a lot of a step of data pre-processing. A major component of that is data anonymization that allows us to actually then make sure that we preserve the privacy and confidentiality of customer data. In the middle there, you see machine translation, where we typically develop and train our own machine translation models. We do very specific, customer-specific models that generate highly adapted translations for each and every one of our customers and their use cases. The next really important piece is proprietary technology for quality estimation. And that's fundamentally where we at runtime, apply judgment as to the quality of the machine translation that was generated on that particular piece of traffic, and decide whether it requires to go to human editing to improve it, or it's good enough basically to go out in pure machine translation form. Then that we finalize that and it goes out basically at the end to our customers. And then what you see here at the far right end is that samples of that go out for detailed human annotation of quality, and that forms data that's really important for us to actually then do this continuous training loop, which involves not just training our machine translation, also frequent training of our quality estimation models, feedback to our translator community. All of those things are part of our continuous training. Okay, so now leading into the topic that I want to focus on here today, which is our work on a neural framework for machine translation evaluation. So why is automated machine translation evaluation so important for us at Unbabel? So more generally, why machine translation evaluations are important. So those of you that have known me know that I've actually worked and been interested and focused on machine translation evaluation, specifically beyond my work for the last 20+ years on machine translation and other problems in NLP. But I've really focused on machine translation evaluation work for a long time. So they are really important because these evaluation metrics really shape and impact significantly the way that machine translation research works, and they also have very, very concrete, important value for us from a business perspective here at Unbabel. So in a more general sense, in MT research, we use them to compare experiments. We use them to decide what works and what doesn't work. We use them to decide whether results get published or not. In machine translation research, typically, the metrics, the standard metrics that have been used, you'd have to show that your new approach is better by at least a blue point in order to hope to get a good publication into ACL or other conferences. We use them, of course, to do error analysis and to identify weaknesses and determine what to work on and to decide which model we want to deploy. Keep in mind that last point in mind, because for us at Unbabel, this is like one of our critical decisions because of our frequent retrainings, is making decisions about which models are good enough to deploy. But machine translation evaluation is a very challenging problem. And I've highlighted here sort of a couple of the main salient points. Typically, machine translation evaluation involves contrasting the output of a machine translation system with a human reference translation under the assumption that that human reference is correct. But a single human reference, of course, is not the only way, the only valid or correct way to translate typically a given source sentence. And then basically assessing based on a single reference translation is difficult. We'll see exactly why or highlight why in a minute. Typically, in critical situations, and we continue, as I pointed out, at Unbabel to do human evaluations. So human evaluations typically are the gold standard for assessing the output of machine translation and of translation in general. But as I'm sure you know, without even me showing here any specific figures, they are extremely costly. They are time consuming. They are not scalable, at a large scale for hundreds of thousands of models. And they're also often themselves difficult, noisy, inconsistent. It's very difficult to get very consistent, very reliable human assessments. So it turns out actually that relatively small amounts and very focused types of human assessments are necessary, but also provide us like the key type of data that we need in order to develop these days much better automated metrics. So particularly evaluation, MT evaluation of Unbabel is a central problem for us because, as I sort of indicated already, we process very high volumes of translations for our enterprise customers using specialized machine translation models for customer service solutions in a wide range of domains. And our machine translation systems are continually retrained to ensure that we maintain the highest quality of translation and robustness to new content that's coming from our customers. And what that means is that we are on a day-to-day basis basically faced with this scenario where we have updated models and we need to actually evaluate them and decide whether that a retrained model is in fact better than the previous version of that model and should be deployed. So this question of how do we know that the machine translation engine A is better than an MT engine B is a problem that we have to actually deal with in a mostly automated way every single day at Unbabel. And we do, so until we develop this new framework Comet, basically, our engineers and scientists were working with existing metrics such as BLEU and METEOR to make those modeling decisions. And we were relying more than we would have liked and on our community of linguists to provide us human evaluations using a particular human assessment methodology called MQM. And because the key of observation of those human evaluations actually generating gold data that has allowed us to do really well in developing much better automated metrics, I want to just give you one quick highlight of what MQM or multidimensional quality metrics is about. This is not a human assessment framework that we developed proprietary at Unbabel. This has been work that's been around, funded primarily by European Commission projects from the last 2 rounds, but many of the labs working on machine translation and on NLP, particularly in Europe, were involved in developing this human annotation framework and mechanism that's known as MQM. And we use it as the primary method for doing human assessments of MT quality of our internal models and systems. And fundamentally, just to give you a hint about what this does is that there's a typology and a classification scheme that allows bilinguals, usually it's done by bilingual speakers, native speakers of the target language, to look at both output from machine translation and also output from human edited translation and identify errors in the translation. They classify those errors according to a typology that distinguishes between things that are important to actually for quality analysis purposes to distinguish. So things related to like whether the errors are lexical in nature, named entities, whether related to fluency, whether they're related to register or style. There's a typology that allows the annotators to mark those types of errors. And then they rank those errors according to, again, a scheme definition as minor, major, or critical. And then on top of that, there's basically a schema that allows to change all of those annotations into a quantitative score that takes into account both the number, the types, and the severity of these errors. And this is, again, has been developed, I would call it a quasi-standard these days in the MT community of using this type of human evaluation, although there's still several others, as we'll see in a few minutes. So at Unbabel, basically, we use both of those types of evaluation, and we've wanted to basically automate this as much as possible, rely on automatic metrics as much, increasingly rely on them as much as we can. And what we were facing before we developed Comet actually was the deficiencies of existing metrics such as BLEU and to a large extent also METEOR. So they're automated, they're fast to run, they allow our scientists and engineers to quickly iterate over MT models. They were good for making development decisions. They're not really good for what we need, once we have MT models in production. They are much less reliable. They're not sensitive to small errors, whereas MQM is more reliable and sensitive, but it's slow, costly, and we can't really afford to do it everywhere where it might be needed. So I wanted to tie this work a little bit again to some of the earlier work that I've done that certainly the faculty at LTI probably remember and know about, but most of the students probably don't know. So I've been working on this problem of automated machine translation evaluation metrics for close to 20 years, I would say, basically from around the time that BLEU came out, and we were not completely happy with what BLEU was already providing from the early days. I started working on this with my students at CMU, and we came up with a metric called METEOR that I'll tell you about just briefly again in a minute. But this slide is actually a slide that I prepared, in presentations about MT evaluations maybe 10 or 15 years ago, and I wanted to bring it up here again because I think the fundamental this identification of what we'd like to have from an automated metric has not really changed. So the primary thing that we want, and where I'm particularly excited about what we now can get with Comet, is high levels of correlation with quantified human notions of translation quality. But these other sort of properties are also really important. We want a metric that's sensitive to small differences in MT quality between systems and versions of systems. Again, this was a big challenge with earlier metrics, and Comet is I would say, quite a breakthrough in this particular aspect. We want a metric to be consistent, so the same MT system on similar text should produce similar scores. We want it to be reliable in the sense that MT systems that score similarly can be trusted to perform similarly in practice. We want it to be general in the sense that it's applicable to a wide range of languages, to domains, scenarios, that basically we have one metric ideally that works across the board. We want it to be not gameable, so not easily susceptible to manipulation and cheating, particularly in like MT shared tasks and evaluations and papers and so forth. And ideally, we want it to be fast and lightweight, so it's easy to run and ultimately incorporable into the way we actually train our MT systems. And I'll say a little bit more about that at the end. So most of the body of work that's been done on automated MT evaluation metrics over the last almost 20 years, I would say, has been following this paradigm of similarity-based MT evaluation. And the idea was to develop automated measures that can assess the accuracy of an MT system by contrasting its output with a human-produced reference translation. And that still is the case, as you'll see with Comet, that's basically what we're doing. But the premise from the very beginning was that in order to get a really good quantified measure of how good a translation is, we would like basically to do that similarity-based assessment according to fundamentally the meaning rather than the surface form of the translation. So the more similar in meaning the translation is to the reference, the better we want to score it. The goal has always been to develop an algorithm or model that's capable of accurately approximating this similarity. And there's indeed been a long history of metrics, starting from very much surface form, lexicalized types of comparison, of looking at unigram and n-gram overlaps, of exact word level matches and lexical correspondences. The ones that have been most salient and used in practice over the last 15 plus years have been BLEU, METEOR, and HTER. METEOR is the one that me and my students at CMU developed. I'll say more about it in just a second. But what we've seen really is an evolution from NLP-based metrics to increasingly trainable machine learning, trainable data-driven metrics. And the most important thing to really point out is that exact lexical matching or surface form matching has always been known to be a very crude estimate for sentence level similarity, and has been really the underlying pitfall of all of the earlier metrics. So I mentioned METEOR. I started working on METEOR in 2004, and I've worked on it with a sequence of master's and PhD students at LTI. METEOR is actually still out there and is still used pretty broadly. We even continue to use it at Unbabel as one of our alternative set of metrics. The main highlights of METEOR, particularly contrasting it with the earlier metric BLEU that has also been the most widely used one, is that it tried to address these issues of going beyond lexical similarity of just unigrams and n-grams overlapping between a reference and a machine translation hypothesis. So METEOR basically was the first to bring in the ability to do lexical matches between translation and references that include semantic equivalence using inflections, synonyms coming from WordNet and other sources, and ultimately paraphrase tables. It was the first metric to really combine both precision and recall, instead of just using precision, which is what BLEU does with what's called a brevity penalty. It separated the tool or the feature used in order to assess basically fluency from what's used in order to assess whether the translation is adequate, and had basically tunable parameters that address both of those things. And most maybe importantly, the METEOR was one of the very first metrics that had tunable parameters that allowed us to optimize its correlation with human judgment. But only a handful of parameters there. So in the early days of machine learning, relatively limited amounts of human judgments, we could get significantly improved correlations with human judgments by tuning those parameters. And the outcome has really been that METEOR has been shown for a long time to be significantly better correlating with human judgments, particularly when scoring translations at the segment level. So METEOR is still around, actually. People are using it. If you look carefully here, it's basically my CMU website that has a sub-site that allows you to download the page. The latest versions that were developed as late as 2014. So my last PhD student to graduate, Michael Denkowski, did a lot of his work at CMU and developed the most recent versions of METEOR. You're of course welcome to use it. It's also been used for a whole range of other NLP tasks. Okay, so fundamentally, what are the primary problems with metrics like BLEU and METEOR that resulted in us developing Comet? Two main things. One that I basically mentioned, but I want to emphasize again. The primary thing is correlation with human judgment. So particularly over the last 3 years, or with this radical paradigm shift to neural machine translation, our MT systems have gotten dramatically better, and these metrics have basically fell behind, and they are now basically they're struggling basically to actually give us reasonable, trustworthy results with respect to how well our models, our neural models are doing. So that's actually really bad news for us at a company like Unbabel, because we rely on these metrics, as I said, to make decisions in model development, and particularly in retraining. And it means that modeling decisions are poorly informed, often don't align, in our case, with human assessment. The cost of verifying and rectifying modeling decisions is high, and the human assessment process is not scalable. And this can result in making poor decisions, and degradation of performance downstream will result in unhappy customers. And even more concretely than that, as I pointed out already earlier, much of the time in developing and retraining our engines, we are actually faced with two systems that are variants of each other. We have an existing model in production, we have a retrained model. Those two systems actually do not differ by that much. So assessing, comparing, doing that kind of model A versus model B comparison with two high performing systems is very difficult, and basically has proven to be completely unreliable with earlier metrics. And one of the key findings of the WMT machine translation shared task a couple of years ago has been that even newer metrics that were proposed over the last couple of years have really struggled to correctly rank high performing systems or outputs from high performing systems. And that's really what we set out to try and dramatically address. So now in more detail about Comet. So Comet is basically the next generation of METEOR, developed as a framework for basically training instances of machine translation evaluation metrics. So it stands for cross-lingual optimized metric for evaluation of translation. And the basic modeling approach in this framework that has proven to be really well is this is yet another application that is able to incredibly well leverage the success of these BERT-like pre-trained language models, large-scale pre-trained language models. So that is, in fact, the starting point. What we do in Comet actually is we start with these large pre-trained language models. We use them to generate word and sentence embeddings, in our case, for three streams of input, as you see there: a source language input, the hypothesis, which is the machine translation output on the target language for that input, and a reference translation. So we generate word embeddings and then sentence embeddings for those three sources of input. We then actually extract some additional features from those embedding vectors to salient features that are designed specifically to help a model learn basically how to predict quality based on those embeddings. And then we pass that on to a final neural network that most of the time, as you'll see, regresses on a score with human assessment data in order to learn basically how to predict that type of human assessment. What I want you to take away from here is that basically that large pre-trained model kind of addresses two main things that really help us in the MT evaluation problem. One is, what it generates, these embeddings are already a semantic space representation to a large extent. What we've been using actually are multilingual pre-trained large language models, which means that the representations that we get across languages, they're not exactly in the same space. They're not exactly in a common, directly in a common space, but they're already in a general space that allows us to leverage the similarity in meaning across languages. So that's one aspect of this. And the other aspect, of course, is the massive language model aspect here. So a lot of the judgments about the fluency come from the scoring of the pre-trained language models that gives us scores about whether sentences are grammatical or are fluent in each of these languages. So here's a somewhat more detailed view about the architecture of this framework. This is our primary type of model that the framework is designed to actually train. So we call it the estimator model. Again, we have basically a source, a hypothesis, and a reference. We basically pass that through the pre-trained encoder and generate the word embeddings and then the sentence level embeddings. This goes through a pooling layer that actually pulls out the representations from several different layers, not just the final layer of the model. From that, we get the final sentence embeddings that we then concatenate into and enrich with these features that we extract from them. And then we finally pass that to a feed-forward network that is then trained with human judgment data. In the case of the estimator model, with a loss function of MSE, basically minimizing the error, the regression error to predict the scores. So here, just to give you a hint of like the features that we enrich this with. So H is the hypothesis. That's what you see here in the middle. R is the reference. And then we, in addition to that, so we have the embeddings from the hypothesis and the reference. We then also do a cross product between the embeddings of the source and the hypothesis. And we have a cross product between the hypothesis and the reference. And then we also have basically vectors that are looking at the absolute difference in the vector, the embedding representation between source and hypothesis, and between source and between the hypothesis and reference. We have a couple of other models or variations on this architecture. So one of them that we call the switcheroo model is actually turned out to be very useful for leveraging more than one reference in cases where we have more than one reference. And in this model, we basically trained the model basically to not know really, or depend on where in the input, basically the reference, the source languages or the target languages. So it basically learns to leverage two sources of information that could be either from the same language or different languages in order to like evaluate this middle input, which is the hypothesis. And that's because we don't actually have training data with multiple references typically to train these types of models. And the last one that I want to just quickly show you here is what we call the translation ranking model. So this is just a different formulation of the architecture where instead of having just a single MT hypothesis, what we actually, in some of the training situations that we have available, we actually have pairs of machine translation where one is, according to human judgments, judged to be better than the other. And so here again, we still use the pre-trained encoder to generate the same type of embeddings for the source and the reference. And we also generate those embeddings here for two machine translation examples. And basically what this model is then trained, the difference here is the loss function, where it's trained in order to maximize the margin between the score of the positive hypothesis versus the negative hypothesis. Now, in the training here, basically, we're not just training this last the regression layer over here, the feed-forward layer, or we're basically fine-tuning all of the models going back into these pre-trained encoders. So we're in the training here, we're fine-tuning all of these components, including the pre-trained models. Okay, so now in this next part of the talk, I basically wanted to show you basically some of the models that we've actually trained using this framework and how well they perform, and then do some deep dive looking at concrete strengths and to some extent still weaknesses of this model compared to previous approaches, and then look at some of the analysis tools that we're developing on top of this. There is, maybe just to give a little bit of background, so the way that we evaluate it, there is a shared task that has been repeated now for several different years as part of the WMT conference on machine translation on evaluating metrics. So we wanted basically to train at least the majority of the models, of the neural models that we train, with human judgments and data that's being shared and released as part of that shared task. And we wanted, as part of this investigation, to actually look and see whether these different types of human assessment actually make a big difference in terms of the model that we train. So how much data is available and is necessary in order to train Comet to actually predict these types of human judgments, and whether, you know, the specific type of human judgment is important. So in the work that I'm presenting here, that was actually presented and reported in a EMNLP 2020 paper that we just presented in November, we trained on 3 alternative types of human judgments. And one of them we use in a couple of ways that I'll show you. But other than one of them, which is this MQM database of human annotated assessments that we had internally in the company, we use publicly available data that's been part of the shared task. So the first one of this is human judgments in the form of what's called HTER, or human translation edit rate. We use 2 corpora that again are available publicly and are used in this shared task. One's called the QT21 corpus, the other one is called the ApeQuest corpus. Altogether, this provides about roughly 200,000 tuples or training instances that have a source input, a reference translation, a machine translation, and then a human editing of that machine translation. So basically the edit distance, which is captured through this measure called HTER, is calculable just, completely calculated directly between the MT and the post-edit. But what you want to basically be able to use is just a human reference, independently generated human reference translation in order to predict from a source and a reference in a machine translation how much editing work is required in order to get to the post-edit. So using this data together, we trained an estimator model that regresses then on these HTER scores, looking at the source, the hypothesis, and the reference, and we call that model Comet HTER. The second variant of Comet was trained on this MQM on a database internally available available to us at Unbabel. But it's a really, I want to really emphasize this. Overall, this is a very small database. It's it ended up being something less than 30,000 examples of tuples from English, in this case, into 15 different languages that were annotated by this MQM scheme that I outlined very briefly earlier. And here the task is you look at the source, the hypothesis, and the reference, and the goal is to predict the MQM score that a human would generate from an annotation. And that version that model we're calling Comet MQM. And then the third source of human assessment data is the one that has been primarily used in WMT, and those are called direct assessments, or for short DA. So every year since over the last 12 years, the WMT shared translation task, news translation task, has done a human evaluation that generates human judgments in the form of direct assessments. Direct assessments basically mean that these are scores that humans provide on a scale between 0 and 100, so it's normalized. And basically they score the overall quality of the translation, on that scale. And then since 2017, just due to the lack of sufficient annotations and that allows for finding majority and cleaning out noise, they've actually taken all the human annotations that are extracted using direct assessment and have processed them into a processed set of pairs of rankings. So that's the direct assessment ranking, relative rankings database that are then used for both training and for evaluation. So we actually trained 2 variants of the Comet model. One trained directly as an estimator model that regresses directly on direct assessments. And the second trained specifically according to that ranking model that I showed you a few minutes ago on pairs of translations that were assessed using direct assessments and then found by humans where one was significantly better than the other and saved as such. So that's the Comet rank model. And in terms of evaluation, we didn't invent anything new here. We basically, again, with the goal of participating in the shared task with Comet, we basically just apply the standard evaluation that the shared task applies in assessing these automated MT evaluation metrics. So that is a segment level evaluation based on these paired rankings. And it's a Kendall-Tao like inspired measure that basically for a test set here for multiple languages with several thousand of examples, typically in the test set for each language pair, it basically measures the number of, on a pair-by-pair example, this is the segment level evaluation, we have the human judgment for that with two translations, which one was better, and we're looking at the metric and saying, does the metric agree with the human judgment as to whether which of these two translations was better? So the Tau measure here measures basically the number of cases where the metric agrees with the humans minus the number of cases where the metric disagrees with the humans, divided by the denominator is just the total number of concordant and discordant examples. All right, so some results. The primary results that I'm showing you here are results from the test sets from the WMT 2019 evaluation. I will say explicitly, you know, this work is from the last year, so we did not actually, Comet was not ready in time last year to participate officially in that evaluation. This is just evaluating, as we developed Comet over the past year, on the training and testing on the WMT 2019 evaluation data. And we extracted here basically both sort of the very fundamental metrics used like BLEU, along with other highest scoring metrics that did officially participate in 2019, and are comparing our Comet models with those other models. And I'm showing you here two tables, one of results basically from into English, so from the data sets that were provided again in the shared task. There's basically, I think, 6 language pairs here, all into English, and then I'll show you results of out of English, from English into other languages. And what we see here is that across the board, our Comet models in general significantly outperformed in almost all cases. One exception here, all these other metrics. This is on the into English. So by the way, these other metrics that are mentioned here, BERT score and BLERT, are 2 other alternative metrics that have been proposed over the last year that are following a similar type of general approach of using pre-trained models and doing some training, or basically using a pre-trained model to do MT evaluation. The results are even more pronounced looking at the out of English language pairs. So particularly the Comet rank model in this evaluation just blew away in those cases all other metrics. It was really, we were extremely surprised how well this actually turned out to work. So we did participate then in the evaluation for 2020 after we developed our initial versions of Comet. I also have some results here. I will admit here that the results are a little bit murkier in 2020. And there's a lot of numbers here. I don't expect you to actually look at this. These are tables that are taken directly from the shared tasks official summary paper that came out. I just wanted to highlight that even though the results maybe were not as conclusive or as strong as we saw on the WMT 2019 data, it's still the case that typically for the majority of the language pairs, one of the Comet models that we submitted was actually the best performing model, in many cases by a statistically significant margin. So this is again into English, and similarly we see a similar picture, actually even somewhat more pronounced in terms of favor of the Comet models going out of English. Okay. So in the time that I have left, I'll try. I want to keep some time for questions as well. Just wanted to show you then some analysis and examples, and some of the work that we're doing on actually building some analysis tools on top of Comet to provide deeper insight. One of the pet peeves that I've had working with my students throughout the years, and those of my students that have worked with me on machine translation know this with me, is I always said that just reporting a single metric number on a test set, it doesn't even matter what the metric is, if it's BLEU, if it's METEOR, and now if it's Comet, doesn't typically provide us enough information, enough insight as to what really is going on and what's working and what's not working. And that continues, in my opinion, very much to be the case. So you can't, if you work with me, you cannot really expect to write a paper and just justify the result that just what the metric score went up by half a point or whatever it went up by. So we looked at some specific things that we expected, Comet to actually be strong. And one of them, Comet is really, so to the best of our knowledge, really the first type of neural MT evaluation model, but maybe the first model in general to leverage both information from the source and a reference translation. There are, of course, there is work on quality estimation where there are no reference translations, where you're trying to evaluate how good a translation is at runtime without access to any correct translation, and that always leverages just the source. And metrics typically leverage only a reference translation. But here we have the opportunity to actually use these multilingual models and leverage information from both the source and the reference translation. And we wanted to know if the source actually is contributing anything, and whether that contribution is actually helping to improve our correlation with human judgments. And so we ran several of these experiments where we actually looked specifically at that. And I'm showing you here the results of the most salient of these, or the most sort of important result that we found, that particularly for the Comet rank model, we ran two versions of that. We trained two versions of that model. One where we excluded the source and the embeddings of the source. We only trained on the reference, so it's comparing the machine translation with only a reference, and versus the full Comet rank model that includes also the source embeddings. And across the board for both out of English and into English, we see that including the source provides a significant boost in this tau correlation with human judgment. So again, this is on this WMT 2019 data. So for the translation ranking model, the source really does seem to be important. And it provides presumably an additional perspective about on the MT through the semantic representation of the embeddings. It does turn out that for these estimator models, the source does not seem to have as much impact. We do see some improvements. They're not always statistically significant. We think that that's primarily because these pre-trained models and multilingual pre-trained models are still not trained fundamentally with an objective to represent the embeddings cross-lingually in exactly the same space, and therefore it limits the amount of information that we can currently extract out of them. So that's one thing that I wanted to show you. A second thing is this issue of how sensitive the metric is, particularly to similar translations and particularly to high quality neural translations. And what you see here in these graphics, actually, this is again was repeated an evaluation that was done as part of WMT 2019, where you extract the segments for evaluation only from the top the top performing models in these different language pairs. And you see the impact that that has then on the ability of the metric to actually make these distinctions according to this Kendall's tau. So what you see here, the graphic on the left is the top models from X into English. The one on the right is from English into X. The red line that you see there is particularly the BLEU metric. And what you see here is that when we extract segments from the top 4 performing systems, basically BLEU loses almost completely any ability to actually make appropriate distinctions between which translation is better and which translation is worse. And for our Comet models, and to some extent also, you see also for these other neural models, BERT-score and BLERT, there is some degradation, of course. It's easier to make distinctions when we have weak systems that are contributing poor translations. So there is a reduction, but overall, you can see that it holds steady, that the levels of correlation are still significantly higher, and in particular, our Comet models do really well in dealing with these high-quality machine translation outputs. A third thing that I wanted to really point out is that now that we're actually in a framework where we're relying significantly on the semantic representations that come out from these embeddings, particularly between the reference and the machine translation, but to some extent, as I said, also from the source. We expected that compared particularly with the lexical metrics like BLEU and to some extent METEOR, the value that would come from additional reference translations in terms of covering the semantic space of possible correct translations would be much reduced, or maybe it would be going away. And in fact, we've seen some validation of that in this analysis that I'm showing you in this particular slide. So what we see here is this is work that was done on WMT in 2019 data. Again, and the data here was contributed by Google and some of our colleagues there, Marcus Freitag. So what we see here is that actually the accuracy and the quality of the reference itself, having a good, correct reference that is a correct translation, both in terms of adequacy and fluency, is way more important now to get correlation with human judgments rather than the number of references. So what you see here in the table on the left, WMT, that line is just a single reference that was generated for WMT, and then they went out and generated 3 additional references. And what they went is also, they went and evaluated the adequacy or the accuracy of those references, because these references are typically generated by crowdsourced communities or to some extent researchers from the teams and so forth. And what we see in fact here is that, first of all, just using a single reference, that's the third column over here. So there is a direct correlation in the results that we get in terms of this tau correlation with human judgments with the quality assessed of the reference itself. So the best quality reference here, which is this one, generates the best correlation, in fact, as a single reference. But then when we use 2 references, then we see some slight improvement from using both of these 2 references here. So here we're always saying, the WMT reference plus one of these other references. But as soon as we use one of the lower quality references, so not only does that single reference result with those lower quality references generate worse results in terms of the Comet model that we train, but even adding it as an additional reference doesn't provide really much significant value. And in fact, here in this other direction, German to English, where there was a single alternative reference that was actually quite a bit worse, it actually got worse just adding that second reference. So more references doesn't necessarily mean a higher correlation with Comet. And what's much more important now, and that actually has significant impacts on our methodology for MT evaluation, is to make sure that we generate really high quality references for evaluation. Okay, and then I wanted just to highlight that we're developing some additional analysis tools. So that if you download Comet, I'll show you in a minute where you can download. Comet is open source. It's freely available with a freely a good permissive license. So you can all just download not just the framework, but also the models that we train. If you want to train your own variant of Comet, you can use the framework to train your own variant on your own data. But we're building then some analysis tools on top of that to allow us to address this issue that I said a minute ago, not just generating a single score on a test set, but actually looking at the distribution of the scores, the segment level scores on the test set. Visually looking at the distribution of scores, comparing two systems in particular, which is always, as I pointed out, the most useful, one of the most useful use cases is to compare system A or system B, or what's called here X and Y. You can actually run bootstrap resampling tests, see the significance of the difference between the results, and look at a distribution here that shows you, for example, system A versus system B on the same test sentences, which ones are better and by which magnitude, and you can then click on these and actually extract examples and see exactly how the changes were between these two systems or two system variants, and get a bunch of useful statistics in addition to just the single comment score. All right, just maybe to finish off, just maybe I'll show you just a couple of salient examples that show some of the interesting things that it does. So these scores that I'm showing you here came from the Comet MQM model, which is the variant that we actually also use internally these days at Unbabel. It's trained on our MQM annotation database. And you can see some nice properties here. I guess this came just directly from training the model, training the metric. We didn't design Comet specifically to do this, but you can see here, for example, that the reference is in fact there's quite a paraphrase going on. If you just look, even if you don't speak Portuguese here, you'll see that lexically it looks very different. The reference looks very different from the MT, but you get a very high Comet score versus a not so great BLEU score, because Comet doesn't in fact punish you for paraphrasing. Comet is sensitive to issues like agreement and casing. It's also sensitive to formality or to register. So you can see that you'll get a lower Comet score just because there's an agreement error, or there's a formality error compared to what the reference was expecting. There's a few more examples of the similar nature. Again, Comet doesn't punish paraphrasing. Comet doesn't mind using synonyms, but it is, for example, sensitive to the right level of formality if there's a difference between the machine translation and the reference. All right, and maybe one last thing to point out, and then I'll kind of wrap it up. We've kind of found that we have kind of a loop that we can leverage here. So even though these gold human judgments are critical for us to be able to train these Comet models, and we don't need very large volumes of examples in order to train them, and they even generalize across languages that we've not seen once we've trained these models. Because these human judgments are often noisy by themselves, we can then take a model that was trained based on these human judgments and then use it to go back to our database of human judgments and detect cases where actually there's noise in the human judgments, and where we actually find discrepancies between the predicted Comet score and the human judgment score. And I have some specific examples here that show where actually there were just incorrect human judgments that were applied. We can use that then to further filter and clean out some of the discrepancies in the human judgments, and then go and retrain and get a better model. So there's some examples of that here. We can always come back to that. Okay, I had a few more other things to highlight, but I think I'm going to basically stop here. Here's a slide that's pointing you to the open source distribution on GitHub of Comet. So, as I said, it's freely available, and both the framework is available as well as the actual model that we trained. And just to wrap up, just a few conclusions. So Comet models exhibit high levels of correlation with human judgments. We found that to be true of all levels, both segment level, system level, and document level. I've shown you focused results here on the segment level. Comet is sensitive to small difference between variants of high-performing MT systems. And the Comet framework does allow you to train custom models and to do further development or to continue contributing to the framework and to the models that we've already trained. And some of the future work and open questions that we're working on, I've already pointed out some of the Comet analysis tools. It is relatively slow, certainly compared to running BLEU. Running a neural model for evaluation is slow. So we're working on ways to make Comet faster and computationally lighter. We are looking at integrating Comet and the framework concepts directly into the MT model training process. And we're looking at adapting Comet also to evaluation of human-generated translations and post-edits in order to help us with our problem of assessing human translations and not just machine translations. Okay, and I will stop here.
Thank you so much.